In this lesson, we're going to explore one of the most powerful tools in science, fitting experimental data to mathematical models. This is how we turn raw measurements into scientific knowledge. So what exactly is data fitting? Data fitting is the process of finding a mathematical function or model that best represents a set of observed data points. This process allows scientists to understand underlying phenomena, validate theories, and make predictions about future behavior. The process typically uses statistical methods, with the least squares method being the most common approach. Here's a visual representation. The red dots are your experimental measurements. The green line is the mathematical model that best fits those points. The first step in any data fitting process is to clearly define your objectives and formulate a testable hypothesis. You need to clearly state what you're trying to investigate. What relationship are you exploring? Formulate a theoretical model that you expect to describe the relationship between your variables. This should be based on existing scientific theory. Let me give you a concrete example. Suppose you're investigating Hooke's law for springs. Hooke's law states that the force exerted by a spring is proportional to its displacement, F equals negative kx, where k is the spring constant. Your hypothesis would be that the force and displacement are linearly related, with the spring constant k as the proportionality constant. Your goal is to measure various forces and displacements, then determine the value of k that best fits your data. The second step is to conduct the experiment and collect your data points. You need to carefully measure your independent and dependent variables. In our spring example, you'd measure different masses and the corresponding spring displacements. After collection, you must clean your data. Check for measurement errors, inconsistencies, and outliers that might skew your results. Here's what your data table might look like. You have masses and their corresponding displacements. Notice how the data appears systematic. Step 3 is crucial. Visualize your data before attempting to fit any model. Plot your independent variable against your dependent variable in a scatter plot. This visual inspection helps you identify trends and patterns. The visualization helps you choose an appropriate model type. Does the relationship look linear, quadratic, exponential? In our spring example, plotting mass versus displacement reveals a clear linear pattern. This confirms our hypothesis that Hooke's law applies. Now we choose a mathematical model based on both our visual inspection and existing scientific theory. Your model choice should be informed by both the patterns you see in the data and what theory predicts. Common models include linear relationships, polynomial functions, exponential growth or decay, and power law relationships. For a linear model, we use y equals m, x plus b, where m is the slope and b is the y-intercept. For quadratic relationships, we use y equals a x squared plus bx plus c. For exponential growth or decay, we use y equals ae to the bx. Now comes the mathematical core of data fitting, the least squares method. The least squares method is by far the most common fitting technique used in science and engineering. It works by minimizing the sum of the squared differences between your observed data points and the values predicted by your model. You might ask, why do we square the differences? Great question. Squaring ensures that positive and negative deviations contribute equally. Without squaring, they could cancel out. Squaring also penalizes large deviations more heavily than small ones, which gives us a more robust fit. Mathematically, we minimize S, which is the sum from I equals 1 to n of the quantity yi minus f of xi, all squared. Here, yi is the actual observed value from your experiment, and f of xi is the value predicted by your model at that same x position. Here's a visual representation. The yellow vertical lines show the residuals, the differences between observed and predicted values. We square these and sum them up. For a linear model, there's actually an analytical solution. You don't need iterative methods. The slope m is calculated using this formula. It involves sums of your x and y values and their products. The y-intercept b is the mean of y minus m times the mean of x. Let's apply this to our spring example with real numbers. Remember our data. 0.1 kilograms gives 2.1 centimeters displacement. The force is mass times g, so 0.1 times 9.8 equals 0.98 newtons. we should convert displacement to meters for consistency. 2.1 centimeters equals 0.021 meters. Using our first data point, k equals f over x, which is 0.98 divided by 0.021, giving about 46.7 newtons per meter. But we have multiple data points, so we should use the least squares method to get the best estimate from all our data. Using least squares on all data points, we get k equals 47.3, plus or minus 0.8 newtons per meter. After fitting, we must evaluate how well our model actually fits the data. The R-squared value tells you what proportion of the variance in your data is explained by your model. R-squared equals 1 minus the sum of squared residuals, divided by the total sum of squares. It ranges from 0 to 1. An R-squared of 1.0 means perfect fit. All data points lie exactly on your model curve. An R-squared of 0 means your model explains none of the variance. It's no better than just using the mean. For our spring example, we might get an R-squared of 0.998, indicating an excellent fit. You should also analyze residual plots. Plot the residuals versus the independent variable. Random scatter around 0 indicates a good fit. The residuals show no systematic pattern. A curved or systematic pattern in the residuals indicates your model is not capturing all the behavior. You may need a different model. The final step is to interpret your fitted parameters and communicate your findings. Interpret the fitted parameters in terms of their physical meaning. What does k equals 47.3 newtons per meter tell us about the spring? Compare your results to theoretical predictions. Does the spring constant match what you expected from the spring's material and geometry? Always present your results with uncertainties. Our spring constant is 47.3 plus or minus 0.8. Let me give you another important example, radioactive decay. The theoretical model for radioactive decay is n of t equals n0 times e to the negative lambda t. N of t is the number of radioactive nuclei remaining at time t. N0 is the initial number of nuclei at time 0. Lambda is the decay constant, which characterizes how quickly the substance decays. To fit exponential data, we often use a linearization technique. Take the natural logarithm of both sides. This gives us ln of north equals ln of n0 minus lambda t. This is now a linear equation. If you plot the natural log of n versus time, you should get a straight line with slope negative lambda. Here's what the linearized data looks like. The natural log of n versus time gives a nice straight line. From the fitted slope, which is negative lambda, we can calculate the half-life of the radioactive substance. The half-life equals natural log of 2 divided by lambda. Let's look at one more example. Population growth in biology. The logistic growth model is P of t equals k divided by 1 plus ae to the negative rt. K represents the carrying capacity, the maximum population the environment can sustain. R is the intrinsic growth rate of the population. A is a constant determined by the initial population size. Population data typically shows an S-shaped curve. Initial exponential growth slows as the population approaches carrying capacity. Unlike our previous examples, the logistic model is nonlinear in its parameters. We need iterative numerical methods to fit it. Now let's discuss the broader applications and importance of data fitting in science. Data fitting allows us to determine fundamental physical constants from experimental measurements. For example, the speed of light was determined by fitting data from electromagnetic wave measurements. The Planck constant was determined by fitting data from the photoelectric effect. Data fitting is crucial for validating scientific theories. If your experimental data fits the theoretical model well with a high R-squared value, it provides strong support for the theory. But if the data systematically deviates from the theory, it indicates the theory is incomplete or incorrect. A famous historical example is Mercury's orbit. Newtonian mechanics couldn't perfectly fit the observed orbital data. This small deviation eventually led Einstein to develop general relativity, which perfectly fit the data. Once you have a well-fitted model, you can make predictions. Interpolation means predicting values within the range of your measured data. This is generally quite reliable. Extrapolation means predicting beyond your data range. This is much more risky and should be done cautiously. Climate models use fitted parameters from historical data to predict future temperatures. This involves extrapolation. Let me warn you about some common pitfalls in data fitting. Overfitting occurs when your model is too complex and starts fitting the random noise in your data instead of the underlying signal. For example, using a 10th degree polynomial to fit just 5 data points will give perfect fit, but meaningless predictions. Underfitting is the opposite problem. Your model is too simple to capture the actual behavior of the system. Using a linear model when your data clearly shows exponential growth is an example of underfitting. Here's overfitting. The blue curve passes through every point perfectly, but it's fitting random fluctuations, not the underlying trend. For complex problems, scientists use more advanced fitting techniques. Weighted least squares gives more importance to more reliable data points. Points with smaller measurement uncertainty get higher weight. Robust regression methods are less sensitive to outliers that might distort your fit. Nonlinear least squares uses iterative numerical algorithms for models that are nonlinear in their parameters. Modern machine learning techniques like neural networks can fit extremely complex patterns in high-dimensional data. A crucial aspect, often overlooked, is quantifying the uncertainty in your fitted parameters. The fitting process produces a covariance matrix that tells you the uncertainties in each parameter. Remember our spring constant? We reported it as 47.3 plus or minus 0.8. The uncertainty is crucial. You should also calculate confidence intervals for your predictions, showing the range of likely values. Let me give you a practical medical example. Drug pharmacokinetics. Pharmacokinetics studies how drug concentration in the bloodstream changes over time after administration. A simple model is C of t equals C0 e to the negative kt, where k is the elimination rate constant. By fitting data from blood samples to this model, doctors can determine optimal dosing schedules for individual patients. This is especially critical for drugs with a narrow therapeutic window, where too little is ineffective and too much is toxic. In the real world, data fitting is rarely as clean as textbook examples. Real experimental data always contains measurement noise and uncertainty. Sometimes multiple different models can fit your data equally well, making model selection challenging. Your fitted parameters must make physical sense. A negative spring constant or a decay constant that gives faster than light propagation indicates a problem. Data fitting is intimately connected to the scientific method. Scientific theory predicts a specific mathematical relationship between variables. Experiments test whether real data follows that predicted relationship. A good fit supports the theory. A poor fit leads to refinement or rejection of the theory. Let me summarize the key concepts we've covered. Data fitting is the bridge that transforms raw experimental measurements into meaningful scientific knowledge. The least squares method minimizes the sum of squared residuals to find the best fit parameters. Choosing the right model requires both physical insight from theory and careful statistical analysis of the data. Always evaluate goodness of fit using R-squared values and residual analysis. The fitted parameters carry physical meaning and should always be reported with their uncertainties. Remember that systematic deviations between data and theory have historically led to major scientific breakthroughs.